Thank you. I know I'm competing with the Kansas City Chiefs, and so I appreciate everybody being here. And I just want to thank Beth and Peter and Emily for putting on this series, which I think is fantastic. And thanks to the museum, who gets the money that we spend on our snacks, so eat up. And I love the museum as well as PINA, Fire Smart, all the different groups that make this island vibrant. So thank you for all of that. And we'll get started. So I'm going to tell you a few stories. And at the end of this talk, you should know a lot about satellites and sensors and maybe a little bit more about me. 40 years ago, I met my handsome husband at the bottom of the Grand Canyon. And then 6 years later, we got married at Grand Canyon. And just last year, we hiked down to the bottom again for our anniversary. And Grand Canyon's a big part of our life. We live in Tucson, Arizona, where I worked for the U.S. Department of Agriculture as a research hydrologist and mentored students. And David was a criminal lawyer, and he also taught at the University of Arizona Law School. 25 years ago, we went to China to adopt our precious daughter, Sarah, and we stayed in China for about 10 to 12 days, where we went to the notary office to do the paperwork, and the hospital, and even the zoo. And we were part of 12 families, all hugging their daughters and wandering the streets in China, causing a scene everywhere. Then 20 years ago, we bought a lot on Protection Island, and Bill Smith helped us build our cabin. And come by anytime for tea. We would love to have you. In 2015, I retired and took a contract with NASA. And I worked with NASA for 3 years with other scientists in Europe, India, Africa, and Australia to work with satellite images. Then in 2018, I retired completely just in time for the pandemic. And that's when Bev asked me to make this talk. And so I thought it would be interesting to tell the story of how we, in the early years of satellites, tried to understand better how to use them. And so it broke out into really 4 different episodes, and I'll go through them one at a time. So signal and noise. Let's start with a bang. This is me and Sarah and Shannon and my mom watching the launch of Landsat in 1999. And that is a Delta II rocket. It's about 40 meters tall, 2 meters diameter, and weighs about 300 tons. And on top of that is the satellite, and it weighs about a ton. And so it gets shoved into the orbit and uses thrusters to try to position itself a little bit so that it actually orbits the Earth every 90 minutes. And then there's a sensor on board the satellite that has solar panels for power, and it measures the radiance of the Earth. So then it transmits that information to the Earth, to stations all over the world, and they all get transmitted to one location, which processes that data and produces these images so that scientists all over the world can look at satellite images. So that amazing process for the Landsat sensor has happened 9 times, starting in '72, with the latest launch in 2020, and producing a 50-year archive of satellite images for the whole world, so that we can do things around the world to help the resources, conserve resources, and better understand drought and flood and other disasters and tipping points. So one day in 1984, I got my first Landsat image. It was delivered by a human postman in 4 boxes with 16 magnetic tapes, and I was able to take those tapes, put them up on my screen, and see my agricultural fields that I was studying on my computer screen. But I had no idea how that image was going to help me with water conservation, which was my job. To put this in context, physics dates back to 300 BC, and modern science dates back to 1700 AD. But remote sensing, what I did was only coined, the science of acquiring information about the Earth's surface, by Evelyn Pruitt, who was a geographer in 1960 when I was 6. And the first Landsat satellite was designed by Virginia Norwood when I was 16. So in 1984, we were just discovering this new technology and women were on the scene. Amen. So that brings me to what we do next, which is we sort out the signal, what we want, from the noise, which messes everything up. And the signal in satellite remote sensing is photons. And Albert Einstein won the Nobel Prize for explaining photons and light intensity. So I don't feel so bad not being able to explain it well myself. But photons originate in the sun due to fusion, and then they stream in waves towards the Earth. And when they go through the atmosphere, they get scattered and absorbed. And when they hit the Earth, they get scattered again back through the atmosphere, and then they get absorbed and scattered through the atmosphere, and finally they arrive at the Landsat sensor. So if I wanted to know what was going on in my fields in Arizona and how to irrigate those crops, I would have to get rid of all that noise, the atmosphere, the soil behind the plants, the adjacent fields, the bias of the sensor, so that I could understand what the signal from the plants was that was telling me whether they need water or not. And that was my job. So what I used in my job was the classic field experiment. And I was lucky enough to be a support scientist in an experiment where we sorted out the signal from the noise from the first Landsat sensors and tried to better understand for the whole scientific community how to use those images. This work was done at White Sands Missile Range. This is White Sands Missile Range. You can see it's very bright and very large, and it's only 10 hours from Phoenix where we worked. So we chose to work there, and this is a security officer on site, and this is what our experiment might have looked like to him. One afternoon, we would arrive with 3 vans towing trailers, 8 students and 2 senior scientists, and we would download all of our gear into this abandoned military bunker, which had electricity and telephone. And despite the fact that it stunk of rancid oil, and at times from that drain in the floor, water bubbled up about ankle deep. So we kept our equipment high, but this was a part of the experiment. So then we would set up our tents and go into town for dinner. Then we'd come back again, and the senior scientists would go to their RV, and the rest of us would go to our tents. And unless the tents had blown away, which they did one night, we came there and there were no tents. So we walked in the direction of the wind with our flashlights, found our tents, brought them back again, restaked them, and then went to bed. So this was just a typical day in the field. The next morning was the day of the Landsat overpass. So we would get up at dawn, look to the sky, and if it was cloudy, we would go home. If it was sunny, we would start to set up our instrumentation. So these are solar radiometers, and they're following the sun during the day to try to figure out how much the atmosphere is absorbing and scattering. And if they didn't follow the sun, we would task a student to force the solar radiometer to follow the sun so we could continue with our measurements. These are our data loggers, which are ancient from the 1980s, and one scientist would set all the times on all the loggers to the same time as the satellites so that we could make our measurements. Then we built these tripods and this piece of metal that holds up this wooden plate. And that plate we actually built ourselves too. And what it does is it reflects the sun almost 100%. So if you look at that plate, it's like looking at the sun. And so we could make our measurements looking at the plate rather than at the sun and see how much radiation actually landed at White Sands. This was another piece of equipment that we built ourselves. Actually, the senior scientists built it to fit on the shoulders of the students. And on the right side is a radiometer, just like the one on Landsat. I mean, it's a Landsat-like radiometer, much smaller. And on the left side is a battery and some lead weights to balance it out. And in the front is a little shelf that we could put our data logger on. So when you add all that up, it adds up to about 50 kilograms, I'm not 15 kilograms, and it begs you to stumble, which we did often at West. Then at the time of the Landsat overpass, we would put on the yokes and we would walk for hundreds of meters in every direction, trying to get the same information that the satellite was getting at the time of its overpass. So we would walk exactly in the orientation of the satellite, 11 degrees east of north, and make those measurements. And then after the satellite passed, we would take all of our data loggers into the bunker and download all of our information, all of the data, make copies of the data, take all the instrumentation, pack it back into the boxes, and put it back into the vans. This was about 2 o'clock in the afternoon at this point. And then we would stuff our sweaty, dirty bodies into the van, and we would drive for 10 hours from White Sands all the way back to Phoenix, arriving home around midnight and go to bed. So in order to keep ourselves awake during that time, we would eat pecan sandies and drink coffee, and we would read the National Enquirer, passenger driver, which explains my great interest in Satanism and Liz, whatever her name is, Taylor. So then we would come back 16 days later, because that's when the next satellite overpass was, and we would do it again. But this time we would take a bucket or a helicopter or all new instrumentation that we would just put out there every 16 days for several years. We did this. So with that set of measurements, we were able to determine how much solar energy came in, was reflected by the clouds, reflected down from the clouds to the surface, and then reflected from the Earth back through the atmosphere again and came to the satellite sensor. And so we eliminated all the noise and determined the signal. And then by doing it over and over again, we were able to figure out what the satellite should be reading at 700 kilometers within 2.8% uncertainty. So we would give that information to NASA, and if that matched what NASA thought the satellite was recording, then everything was good. If it didn't, then NASA had work to do. What wasn't part of our experiment was all the mistakes we made, which at this point we took the Landsat-like sensor and dumped it straight down into the sand, filling it with fine sand. Other times we would arrive and there was water on the site, or snow, or missiles. It was a missile range. Or sometimes we would forget our cables or our instruments or our badges that got us onto the site, or get a flat tire on our way to the site. And so all of this was what happens when you run a real-time experiment in the real world, and the senior scientists were full of forgiveness, which taught me a lot. And they often said that mistakes are opportunities, which again taught me a lot. So back to my cotton field again. Now that I had done that, I was able to look at that image that I had on my screen and know what those cotton plants were telling me, because I knew how to eliminate all of the noise in that image and just get the signal from the satellite. So what did I learn? I learned to sort the noise from the signal and forgive, and remember that mistakes are opportunities. So I am going to pause. Whoa, because I'm not going to pause. Okay, pausing. Oh, I think I messed up here. Okay. Just to take a drink of water. Anybody have any questions? Otherwise, I'm going to carry on as fast as I do, because that's what I do for a living. Sure.
One. Landsat was, I'm sorry, the date again for Landsat, the first Landsat?
72.
What was the earliest satellite? launched. There was satellites launched before.
Oh, yes, absolutely. I don't have any idea when the, what?
68.
Oh, I don't know when the first satellites. These are the, there are lots of satellites up there, which I'll show you at the end. But the satellites that I'm looking at are what are called Earth observing satellites. And they are the ones that scientists use to try to help the Earth be better and cleaner. And
I was just asking about the primitive launch.
I don't know the date. I apologize. And no more questions, only one. Okay, go ahead.
Why piece of wood on a mirror if you try to reflect, measure reflectivity? Wood would absorb part of it.
Say again?
You use a piece of wood to measure reflectivity. Why?
Oh, we used it because we could paint it with barium sulfate, which is a highly reflective paint. And not only that, but it allowed it to be Lambertian. So no matter which way we looked at it, it was always the same 98%.
I only got the wood part.
I didn't mention it. Okay, all good. Let me get another drink of water. Okay. I get this now. So independent and dependent variables. All experiments seem different, but they're really all the same. There's an independent variable, which is the cause that you try to manipulate. And then there's a dependent variable, which is the effect, which you try to measure. An example that I thought of is, let's say you feel kind of broke and you stop spending as much, and then you go look at your savings account, you're not quite as broke. And so we all do experiments every day in our heads. We're all scientists. But all experiments are inspired by an unanswered question. That's why you do the experiment, and that's why you look for a cause and an effect. So in 1985, there were two experiments that were conducted by by Ray Jackson, who was my boss, and Alfredo Huete, who was my major professor in college. And these two experiments influenced how I did experiments for the next 30 years. So I wanted to talk a little bit about them. So what we know is that here's the sun, it's sending a beam down. The beam that ends up at the satellite is a combination of the reflected radiance from the leaves, the stems, the bulbs, the flowers, soil, water, weeds, everything that is on that surface. And generally, what you want to know is maybe what the leaves are telling you, because the leaves kind of tell you whether your plant is healthy or not. So you need to eliminate all that other, all those other signals. So rather than use the satellite, a lot of scientists would take the same sensor, a similar sensor to the one on the satellite, and hang it from a boom and make boom-based experiments, and they were more easy to control. So the one I'm going to tell you about is an experiment was by Ray Jackson and Elaine Ezra, and what they wanted to do was figure out how would leaves look if they didn't have enough water, and what would the satellite be measuring on those leaves that didn't have enough water. So rather than use the satellite and use the whole field, they used just 2 rows of cotton, and you can see they staked those cotton plants with stakes, tied them up, and then they cut 1 row at the bottom so that it wasn't getting any water at all. And then they moved the boom-based sensor back and forth and measured the radiance from those leaves. As you can see, they're starting to brown every 10 minutes. And then they could tell what the satellite was measuring because they had done this on the ground. And they were some of the first scientists to understand how the satellite would respond to leaves that needed water, which was what farmers were interested in. The second experiment was kind of the inverse. They left the plants as they were and changed out the soil. So you can see they've got these cans of soil that they put underneath the plants because the soil in Georgia is different from the soil in Arizona, even though they're all growing cotton. So they again took a radiometer and made measurements over all these different plants through the entire growing season while they were changing out the color of the soil. So that way, when the satellite came over, they could say, oh, okay, well, I know how to minimize the influence of soil so that I can maximize the signal from plants. And again, this was one of the first experiments to do such a thing and was very well received. So during my career, I decided more was better. And there were a lot of satellites out there. And so our team started purchasing satellite images. We purchased 39 Landsat images and 50 images from other satellites, all delivered to my office, costing in today's dollars, millions of dollars. And then we would support them with airplanes and helicopters and powered parachutes and robots and a guy laying in a ladder hooked to a forklift. Anyway, so we were trying to support them underneath. Our field site was the University of Arizona Maricopa Agricultural Center, which I'll call MAC from now on. And this was a farm where the manager kept meticulous records of what was planted, when it was planted, when were things harvested, when did he water, and then he would also manipulate variables at our request so that we could get the right variable manipulated. The fields at MAC were very large and very flat, which made them really perfect for remote sensing measurements. And so at MAC, it was like a remote sensing mecca. People came from all over to make measurements of everything you can imagine. Sometimes there were 20 scientists gathering in the morning before going out to make their measurements of leaves and gas exchange, evapotranspiration, photosynthesis, root hairs, yes, and the gas exchange in the atmosphere, the relative humidity, the temperature of the plants, all these things people were measuring. And so if I was interested in crop irrigation for my field in Maricopa, telling the farmer when they should irrigate or not, then I might be measuring soil moisture while the satellite passed over. And then I would partner with the other scientists who would be measuring plants. And if they were interested in plant photosynthesis, they would partner with me because I could hold soil moisture constant. So you see there's that manipulation of variables, trying to answer unanswerable questions. And everyone was there because they had their own separate question that they wanted to answer. But just like White Sands, things didn't always go as planned. So on dove hunting season, we arrived to find people with rifles surrounding MAC, ready to shoot doves. And so we compromised with them, and they got MAC in the morning and we got MAC in the afternoon. So all of these questions, I keep talking about unanswered questions. NASA was launching, here's 3 satellites that NASA launched during that period alone. The Japan Aerospace Exploration Agency started up and they have a satellite up. The India Space Research Organization partners with NASA to launch satellites. The Canadian Space Agency, which you'll hear about more in this talk. And then the European Space Agency, which launched a entire constellation of satellites. So what did I learn? I learned that scientists investigate cause and effect, and they discover what is new and surprising, like we all do, so we're all scientists. Okay, one more question and more water. And people can get up and get a cup of coffee, and I know I talk fast and I go over a lot of stuff, but just do what you need to do. Okay, now we're going to get technical. So strengths and weaknesses. I'm going to take a little divergence here and talk about plants for a minute, and then I'll get back to satellites. So plants need food and water to live, and if they don't get it, they die, and they're kind of like dogs in that sense. But the cool thing about plants is that plants make their own food through photosynthesis. So they take energy from the sun. It gets absorbed by the chlorophyll to make energy for the plant. They lose carbon dioxide and water through their pores, just like our pores. And then they pull water and minerals from the soil into the plant, and the water combines with the carbon dioxide and it makes glucose, which is their food. So this is how a plant looks to a dog lover and a physical scientist who doesn't know much about plants. If they don't have everything they need, just like a dog, they will tell you in a very silent, coded language that you have to decode. And so the electromagnetic spectrum is the best decoder for plant signals. It has many wavelengths. It goes all the way from gamma rays to radio waves, where gamma rays have wavelengths as narrow as a picometer, which is a trillionth of a meter, to radio waves, which have waves as long as 1,000 meters. And so you can see that there's a lot of wavelengths in there that can tell us what the plant is trying to tell us about food. And every satellite, Earth-observing satellite, is measuring energy in the electromagnetic spectrum. So it's very, very powerful. So what the satellites do, what makes one satellite different from another, is they filter the electromagnetic spectrum into bands that they find have a strength or a weakness that can be compensated with another strength. So for example, Landsat filters it to blue, green, and red wavelengths. It also has and a near infrared wavelength. It has 2 bands in the shortwave infrared, and it measures the thermal wavelengths, and has now added a panchromatic band, which is like a black and white photograph. And there are other satellites who break the electromagnetic spectrum into hundreds of bands, 200 very narrow bands. There's also satellites, particularly the Canadian satellites, that work in the radar bands, which we'll get to later. So as Bev said, I was part of these NASA science teams that were selected to help NASA understand the strengths and the weaknesses of their satellites for different Earth applications, such as agriculture, in my case. So they would have me on there to talk to them about agriculture and how these bands might be useful. So I'm going to take you on a tour from one end of the spectrum to the other and talk to you about strengths and weaknesses. And I'll start with Landsat, which has blue, green, and red bands, and a near infrared band. So here's a plant. The energy comes from the sun, and it just so happens that leaves reflect highly in the green and the near infrared, and they absorb the red light for photosynthesis. So that's why plants look green. That's why leaves look green. So if you wanted to study if this was a healthy plant, you would take the ratio of the near infrared reflectance over the red reflectance. And you can see that if near infrared is high and red is low, it would be a very large number, whereas if the plant was unhealthy, it would be a very small number. So it enhances the information if you use the simple ratio. It's so popular that NASA puts out a image. This is an image of Mac, where the red fields are green, they're cotton fields. That's the way they color this stuff. And the blue fields are bare soil. But people have used the simple ratio for many, many things, including a joke that the simple ratio was good for predicting the number of nuns in Chicago. And that was at a conference to tell us all to be more careful. So another part of the spectrum that we work in is the thermal spectrum. And that's really just the temperature. So anybody who's gone through the pandemic knows about tax, and they're able to take your temperature without being in contact with your face. Well, the thermal sensor on Landsat is a lot like a tax. And so it gives you an image of the temperature of the alfalfa fields and cotton fields. So again, it's pretty simple. The solar energy comes in, it hits the plants, they go through photosynthesis and lose a little bit of water, and it cools the leaves. So plants that are healthy are cool, plants that are unhealthy are hot. So if you looked at a satellite image, you would see that difference. This is another image of Mac, and the blue fields are cool, and the orange fields are unplanted, they're bare soil. So you can see that even in the blue fields, there's a lot of variation in that blue, a little bit of green. You can see areas maybe that needed irrigation or that had a soil nitrogen deficiency. You can just see how much information is in a single image of a agricultural area. And this is the thermal, which looks very different from this image things with simple ratio. So now we're going to go on to radar, which is another wavelength in the spectrum. And this is the one that the Canadian sensor measures. So picture this, there's a satellite. It actually sends its own signal down. We're not talking about the sun anymore. So it sends a signal down, and then it continues to orbit, and it retrieves that signal at a later time. So it's kind of like a guy throwing some balls at a sponge and trying to figure out how long it took the balls to get back and how many returned. That's what radar is like. But what's really nice about radar, so it's going, actually it's a wavelength long enough to go actually through the plant and measure the soil. It can actually go through clouds, so you can do it on a cloudy day. And since it's making its own signal, it can do it at night. So there's a lot more strengths to radar than to some of the other optical sensors that I've shown you. So here's a radar image. And as I've labeled this section, it's strengths and weaknesses. Well, you can see there's many different colors here, and what my students found, unfortunately, is that, let's say field 35 there is a cotton plant, a cotton field. Well, this area on the right under field 11 is buildings, and they have the same signal. So radar is very sensitive to roughness as well as soil moisture. So we went back out in the field to do a signal and noise experiment again, but this time not at White Sands, this time at Walnut Gulch Experimental Watershed, when there were a lot of animals out there and a lot of flat tires. So the last index that I want to talk about is related to the hyperspectral. And if you remember, I told you that the hyperspectral is many, many different bands in narrow wavelengths. And so here we're back to our plants again. And here's the energy from the sun coming in, and photosynthesis happening. Photosynthesis is really what all farmers want to know about. And when the plants use energy for photosynthesis, they emit a little faint fluorescence or glow at a longer wavelength because they don't need all the energy they've got and they have to get rid of it. So they have this glow that is measurable from satellite when they're doing photosynthesis, which is different from all the others. On the simple ratio, it's only measuring greenness. The temperature was measuring transpiration, and the radar was measuring soil moisture, but SIF, the solar induced fluorescence, is measuring photosynthesis. So it's really an important index and would make a huge difference in the world and in farming. The problem is that it takes a very special sensor to measure that very faint signal, and there is no sensor out there that measures it right now. This is the Flex sensor that will be launched in 2025, and it will be the first sensor to measure SIF. So that will be a big day. Watch your news feeds for the Flex launch. So anyhow, in 2015, one of my students decided she wanted to do an experiment in SIF, and it was the last experiment I did in my career. And we went out to this field, this wheat field at Mac, and tried to measure SIF, and she borrowed a whole bunch of instrumentation from her friends in Europe, bought some from Amazon, solicited the help of me and another student, Guillermo, and we went out to this field every week, all winter long, rain or shine, and it was very grueling work with 20 pounds on our backs and doing mathematical equations in our head, and it was a tough experiment. Well, we finished the whole experiment and we found out that we had set one setting on one instrument incorrectly, and we threw the whole thing, every piece of it. None of it was useful after that. So Maria Pilar decided to do it again. So the next winter, we went back with the same instrumentation, the same people, the same sweat, the same sun hats, everything, and we were 100% successful. And she was one of the first scientists to understand how nitrogen affects the signal. So, what did I learn from being on science teams? Strengths and weaknesses, solve problems, and if you fail, keep trying because the stakes are high. Okay, the last episode. And you can get up and stretch even. Any questions?
It sounds like a simple question, not a silly question. But does it matter the difference in the color of the plants themselves, the leaves?
Yes.
We're talking about green.
Yes. Yes, you're absolutely right. So I have been concentrating on cotton here, but at the same time we were making the cotton measurements, we were making measurements in alfalfa. And we were making measurements in tomatoes. And I mean, every one of them is different. And actually, that's a perfect lead in to this next. Because essentially, you know, if you've got all these different plants and you've got all these different colors and you've got different satellites, you're looking for some generalization or some pattern because you can't know every single plant in the world and how it would look to the satellite. So this will talk a little bit about what we do next after we make all these measurements. Thank you. Oh, and I'll give a shout out. When's your talk? The 19th. I wish I was going to be here. Okay. Sure. Okay, so patterns and generalizations. Essentially, like Helen said, patterns kind of make sense out of the complexity of satellites. A pattern is something that is in common across situations, maybe different plants, and a generalization is when they have features in common. And the cool thing about generalizations is they lead you finally to predictions. So we're back to our nuns in Chicago. So the scientist said that he found a correlation between the simple ratio and the number of nuns in Chicago. And that was silly, but it was a finding and it was statistically significant. Now, if we had found that same finding in different cities like Paris and Vancouver and Los Angeles, then that would be a pattern and it would be something to look into. And then if that could be validated with theory that made sense, then you could generalize it and you could use it for prediction in anything. None of that happened, of course, because it was a joke to begin with. But the idea of finding generalizations and patterns stuck in my head, and it led me to a sabbatical that I took in Japan in 1993. And that's Yoshio Inoue, I was there working with him. He's with the National Institute of Agro-Environmental Sciences. And there I was in a country where no one spoke my language, and I couldn't even read their language. And I was in a small office that had no internet. So I had a lot of time to look for patterns and generalizations during that month. So I arrived to work with Yoshio. And this too, you recognize these. This is the simple ratio and the temperature at MAC. And you can see I put a grid on them because satellite images are actually a whole bunch of pixel elements called pixels. And if you can take those two images and you can plot them one by the other and get a scattergram, which we did. And you can see that it has sort of a pattern. It has kind of a warm edge that I used a red line on and a cool edge has a over on the other side. And the simple ratio is taking you from bare soil up to full covered vegetation. So that's a finding. Well, look, we did this and this is what we found. But then we started to do it every few weeks as the satellite came over. And we found that it repeated itself but it shifted to the left and the right and up and down a bit. And so we couldn't really understand it, but we saw that it was a pattern, and people all over the world were finding the same pattern for temperature and the simple ratio. So we decided we would try to generalize this. And so we turned to known theory that would allow us to compute the temperature knowing only meteorological information and some field information. And these fellows here were the developed that theory, so I don't take any credit for that. I was just applying it. So we took the theory and we tried to compute 4 points in this box. And that would be for full cover vegetation, the wettest and driest, and for bare soil, the wettest and driest, because the extremes are always easier to compute. Then we took further theory and said, well, this could be, these 4 points could be connected with straight lines, which gave us a trapezoid. So now we had a theoretical shape that fell on top of the scatterground, and it changed with time because the weather was always changing. And so, so we now had a generalization of this pattern. And how does that work for my farmer who's trying to irrigate his crop? So imagine that you get your first satellite image, and in your field, you know what the temperature and the simple ratio is on that day for that field. Then the next day, you get another one, and it starts to green up. So it starts rising, and it starts to warm up because you're not watering it. And it starts to get towards that warm edge. And when it does, you say, this must be the day I'm supposed to water. So you water, it gets cool again, and it continues to get green. So you can see that using that, you're able to actually make a prediction on when you should water your crop. So if you colorize the trapezoid, you can see you can make a map of which fields need to be irrigated. So the red ones are areas that don't have any crops in them, but the green and yellow are areas that maybe had just been irrigated or needed to be irrigated, or maybe were irrigated, but the water didn't even get there and you wouldn't have known it unless you could look at your satellite imagery. And so this now, the generalization had led to a prediction, and now a satellite image was actually giving real information rather than information about radiance. So we named it. We called it the Water Deficit Index, and we hoped that people around the world would start using it. And so we did this, Yosho and I, with 2 other scientists, Alain Vidal in France and Tom Clark in Arizona. And since we were in Japan, we would work for 8 hours and give our data to Alain Vidal, who was just starting his day. And then he would work for 8 hours, give his results to Tom, who was just starting his day. And then he would give his results to us in the morning when we woke up. So it was like working 24 hours straight, but getting some really good sushi dinners in the meantime. So, so that's how we did it. So then Yosho, Alain, Tom, and I told our story, which is what scientists do. So that's what this whole talk is about, is telling stories. We published a manuscript that had the 15 equations we needed to compute the water deficit index, 18 more in the appendix, tons of scientific and technical notations with lists of all of our assumptions, requirements, and constants, possible errors, and a demonstration of the approach so that somebody else could do this at their site and validate our results. So I would like to say that now the water deficit changed everything, and farmers are all using satellites, and they're making money, and they're not using their farms, and well, it didn't work that way. Because many reasons, but the satellite doesn't come over often enough to actually make decisions. And the farmers, even if they had perfect data, they oftentimes can't get water when they want it exactly, and so they couldn't actually follow it perfectly. But it was used. The water deficit was used for malaria risk in Africa and for forest fire risk in France and grassland degradation in China. So it was being used for many different things that we hadn't expected. Then in 2016, the water deficit was used to schedule irrigations for plants in Denmark, used for irrigation scheduling. And that was 25 years after we discovered it, and now it's being used. And then in just this year, it was used for scheduling irrigations in barley in Moran. So we're pretty happy that it keeps moving. So scientists, if they tell their stories, they often get awards. And the biggest award of all, which is money to hire students. And students do the best work, and you get to put your name on with them, and it's a win-win-win situation. So what did I learn? So I learned that stories build on stories, and I hope that we all tell our stories. So when Bev asks you to be part of the speaker series, you will say yes. So now we're coming to the end here, and this is an image, it's actually a simulation of what all the satellites in the sky would look like if you could see them all. And there were times at MAC where I would lay in a fallow field, and I knew what time my satellite was supposed to come over, and I could watch it go overhead. And so I hope that you will take a moment and go out on a clear night and look up, and you will see a satellite going over. And I want to finish here. It's a shame that, well, you'll have to just figure out where these things are. I'm going to finish with some satellite images because, as Bev said, 40 years ago, I saw my first one, and it had a great impact on me. So enjoy.